Stokes from the University of Manchester, and that's her title. I know. There you go.
Okay, so I'm presenting the simulation of bent core molecules using molecular dynamics. So generally when we think of like liquid crystals, we think of particles that are like rods or disks, and general phases we'll think about like pneumatics and symmetrics. But the phase that in my group we've been interested in is the biaxial pneumatic phase, and this has a second orthogonal alignment director. And the reason we're interested in this phase is because it's proposed that it'd be good for like a faster alternative to a uniaxial twisted pneumatic in liquid crystal displays. It's got 3 orthogonal axes, and that's what can make it like a faster, because it's only like 120 degree difference. It's got less rotational order than the uniaxial pneumatic. So one of the proposals for doing this is to use bent core molecules. These have been suggested as a superior candidate for the formation of a biaxial pneumatic phase because it's biaxial shaped in itself anyway. And the degree of biaxiality is governed by the bend in the angle. This is just like an idealized phase diagram, which is like so it shows like the narrowing of the internal angle as a function of density, and it shows like different phases that can form. This has come from Onsonga theory, I think. So we've got like rod-like pneumatics, disc-like pneumatics, and then we've got this like minor region where a biaxial phase will form. Then we have like an isotropic region. Within our studies, we've used molecular dynamics, and we've used the repulsive Weech-Handler-Anderson potential for this. We're using like hard sphere chains to represent the bent molecules, and these are like equal at size, so like the middle ones where the bend is. So it's like an odd number of beads are in the molecule, and the like center one is like where the bend occurs. If it's completely flat, then we have like a 180 degree angle, and if it's like straight up, then it's like perpendicular, and that will be a 90 degree angle. For the actual simulation procedure, DL poly has been used, which is like a molecular dynamics package, and we use the Wöhler integration algorithm. We use a cubic simulation cell with periodic boundary conditions. The molecules were placed on this cubic lattice such that there was a density of 0.001. When we ran the MPT simulations, we used the Nose-Hoover thermostat. And initially what we did, we generated like a system with like a number of bent molecules in. And then we run an MVE run, which gave us like an isotropic gas phase. And then we applied like constant pressure. So we did MPT simulations. And then we just varied the pressure in small incremental amounts to change the phases using pressure. So this is previous work that was done before I started by Robert Sargent, who's like left the university now. And he investigated single bent core molecules and single mixtures. And this is one of his results for like 11 bead model with angles less than 135 degrees. So here you can see like clusters are forming. It's just like a cluster formation, and like when we go even further down in angle, it's like even less of just smaller amounts of clusters. The clusters that are forming are a lot smaller. Once theta is 140 degrees, you can actually see phases are forming. So we've got like an isotropic phase here, and then a pneumatic phase is formed here, and then we're getting like a symmetric phase forming here. So the pressure is like once we've got to a bend angle of 140, phase transitions are occurring. So yeah, just like what I said, if the angles are greater than 140, we get the phase transitions, and if they are less than 135, he found that clustering behaviour was formed. There wasn't any global director when the clusters formed. And we didn't get to the point where the actual bend, like the theoretical bend angle for biaxiality is around 110, but we couldn't get to that point because phases wouldn't form when the angle was less than 135. So the project that I've been working on is to try induce a biaxial pneumatic phase in like bent core systems. In this way, we're concentrating on using like a polydispersed mixture of instead, so like using 4 to 6 components which had different bend angles within them. And the reason for doing this is because we wanted to try to destabilise the symmetric phase. So in the system, I had 11 molecules in each, 11 beads in each of the molecules, and I varied the number of different bent cores in the molecules, so they could be like 4, 5, or 6. The total number of molecules were either 900 or 1,000, and that's because I used like equal numbers of like molecules in the system. So like if I had like a 5-degree difference, it'd be like the equal amount of each, really. So I've ran it for a few different systems, and I'm just going to show you some of them today. So I've done like 4-component systems. So here I had angles varying between 135 and 150. So in this case, I had like 1,000 molecules in the system, and I'd have 250 at 135, 250 at 140, and like so it followed that pattern. For the 5-component, it's like the same sort of pattern, except it's like 200 molecules because it's a 1,000 molecule system. For 6, it was like 150 of each, so it ended up being a 900 molecule system. And then for the 4 components further down here, it was like the same, except for these last 2, which they went up in like increments of 10 because I decided to like change, like see how far I could spread the angles. So the 5-component system, this is just the plot of the order parameters as a function of the pressure. So you can just see that it quite soon rises to like a pneumatic type phase, and then it comes up to like a symmetric phase, and this is just it becoming crystalline. This can just be seen in like the images here, so you can like see the transition. I should probably mention about these images, these like represent the average order. So if it's blue, the molecules are lining to the average. And if it's like red, it's like perpendicular to it. This is the same set of images, but here what I've done is I've coloured each of the individual molecules, and the centre like apex is been like made brighter, so you can see where the centre atoms align. So you can just see here how it's like isotropic to pneumatic, and that's still like a pneumatic phase, and then how it becomes a symmetric phase. For system 3, we have the 6-component system. So here we like go up to like a pneumatic phase, but then here we ended up having like a biaxial symmetric phase formed, and then it went back down to a symmetric phase. So this is like shown in the images here. So we've got like the pneumatic, isotropic, pneumatic, and then this is where the biaxial symmetric formed, and then this is when it became like just a general symmetric phase. And then this is the same image represented in the actual physical molecules. This was system 4 was when I went down to like a smaller angle range. So like the maximum angle here was like 135. And when I first ran this, I ran it in like increments of like, well, I was working in kilopascals at that time, so it was like increments of 10 kilopascals. And it just formed like lots of small clusters. So I ran it in like smaller increments, and it just like shows this rise in both the parameters together. And these are like the physical images. So from like quite a high pressure, you could just see like large clusters are forming, and then we got like this part where it's like a perpendicular part, it's like formed in the middle, and then it's just like squashed in. So it's like a mixture of like perpendicular and parallel, really. I did rerun it again. This is just the actual images of the. I ran it again with more pressure steps earlier on, and this has changed it slightly. It's raised the order parameter again to like 0.8 on this occasion, and it's a little bit less. It's still like clusters, like larger clusters forming now, but the order parameter is like stating that there could be like some global order within the system, so it's quite confusing what's happening with this system. The other systems that are similar have followed like the same sort of pattern. I've not run them in like smaller increments yet, but they've all started off with these smaller clusters. So the expectation is they're probably going to follow what this one's doing. And this is just like the image when it's like the actual coloured molecules, so you can see like this one's like all pointed in different directions. This is the first one where it's like a lower type angle, but it's got like ranges of like that vary in 10, so it stays like constant for a while, like an isotropic phase, and then it starts to increase. And the actual system images are quite strange. So we seem to have like an isotropic phase, and at this point it's still quite isotropic, but it looks like it's forming like clusters. And here it's kind of like starting to form layers, so it appears, it's easier to see in this next one, it appears to like be forming clusters and not showing, I haven't seen a nematic transition in this one yet. And it just seems to go directly to like more like a symmetric from a clustering phase. So I probably might need to go in like smaller pressure steps still. But I've just not actually seen the nematic phase form in this one. When I increased it by a factor of 10, like the degrees by 10, so it started at 125 instead of 115, we actually see that phases are actually forming again. So it's like demonstrates like the difference between like how 10 degrees can vary it by so much really. So the actual physical images, you can actually see it's like a proper system again. It's like an isotropic to a nematic, like a clean nematic to like symmetric. And then this one, we actually see that the mixture we actually get a demixed symmetric in this case, whereas in all the other cases, all the components have just been like mixtures, so they haven't. So the summary is like the 4 to 6 component systems with bend angles that have been greater than 140 have been found to have like phase transitions. So like for the 5 component, we've had isotropic nematic symmetric. 6 component, we've had the same but a biaxial symmetric in the middle. For the angles of 115 to 145, it's like I'm not sure if there's like an isotropic then a clustering into a symmetric, or if there's a nematic phase somewhere within there. There's been for the 125 to 155, we got the isotropic nematic symmetric again, but then a demixed symmetric. And then when the angles were less than 140 degrees, we found that clustering behaviour that was seen like in what Rob was doing with his single components was occurring. So it's just wondering whether I should go in like smaller increments now. So because as I've been going smaller, I've been getting larger order parameters and like larger clusters really. And maybe the system just requires more equilibration, or it's stuck, it's jammed in some way. We haven't defined a biaxial nematic yet by using more components. I've seen the biaxiality in the symmetric for the 6 component system. The 4 to 6 component mixtures are surprisingly seem to be very stable. I mean, especially when I did like the 10 degree angle at 125, it clearly formed like ordered phases. There's got quite a lot more work to be done on the angles that are at smaller angles to see if I can get them like fully equilibrated and stop this clustering from happening. Thank you.
Do you have any questions from?
Did you try simulations with static dipoles too?
No, I've not done any dipoles yet. No, we're just looking for like suggestions of what different things we could probably try while we came here. Yeah.
Electrostatic dipoles seem to enhance stability of biaxial order, at least density functional type of calculus suggests something like that.
Okay.
Yeah. Could the clustering be sort of some attempt by the system to phase separate? I mean, maybe one would. I mean, you're finding it between the isotropic phase and the symmetric phase, right? And clustering.
Yeah, for that 7 component one, I never get to a like symmetric phase with those smaller angles. It was just that one system.
But clustering means kind of light particles are hanging around with light particles?
No, it's not generally. They're generally mixed in the clusters. Is it that way?
So
Find one of the cluster ones.
show us a cluster.
Yeah, see, that's like one where clusters are forming, but if you look in the actual images of the actual molecules where they're coloured, you can see that they're not like linked molecules together, it's just clusters
What, I mean,
that aren't the same molecule.
could one sort of figure out what might be going on by going to larger systems and seeing what features were, retained?
Yeah, I could probably look at larger systems. I don't know, I'm not sure if Rob did look at larger systems, because he's had clustering as well in the spot, like with just one component, he had the clustering as well in these smaller angles, so it just seemed to be a common thing.
Mark?
Just while you have your clusters up, Christine, so you talked about the uniaxial phase of clusters and things, and of course there's this nice prediction that some of us talked about earlier in the week, that you might be able to get a uniaxial phase going through a first order transition to another uniaxial phase with clusters. So I just wonder if you got that, and or could look for it in the systems that you've got. So that would be a kind of nice prediction that theory had made.
So what's that again, sorry? It's
Well, you already have a uniaxial phase with cybertactic clusters in.
Yeah.
But there's this theory by Professor Vanagaris and Professor Patinas in Patra that you could have the possibility of having a transition from just a normal uniaxial pneumatic phase, first order transition to another pneumatic phase, but with these cybertactic clusters, and then maybe even a transition to a biaxial phase, pneumatic phase. But there's this definite prediction that you should have uniaxial to uniaxial phase transition. So you could probably, it might be something you could look for if you haven't seen it in some of these systems.
Yeah.
I have one more quick comment as well, and you won't want to hear this because you've already got a wide parameter space, but one thing that's also possible, of course, is that you could have a little bit of flexibility in these rods, just by making, for example, the tails a little bit flexible. Yeah. And that in itself kind of introduces polydispersity, at least in polydispersity in molecular shapes. Yeah. So that's another possible way in which you could kind of, slightly reduce the stability of the smectic phase, possibly relative to the biaxial pneumatic. And it kind of also has the added advantage that it might be easier to equilibrate.
Yeah, it might be. It's quite tough to equilibrate. It can take forever.
Any other questions?
Just a curiosity, maybe the second or the third model you showed had this smectic transition at high pressure, going from a system with high biaxiality to a system with zero biaxiality. That,
I've got the wrong way there, sorry. Yeah, this one.
That one, and that passed from a smectic where you didn't have phase separation between different species to another one with zero biaxiality where, if I'm not wrong, you had the phase separation between species, or more or less. Could you comment on that? Because you didn't see this kind of behavior in the other models. So why did it happen here and not in the other ones? I mean,
I don't have any idea why it happened. It didn't happen in the 4-component mixture. It's only this one that I found like a peak in the biaxiality and then it goes back down again. I have no idea why it's occurred or...
There are no more questions. Thank Christina again.